Hello and welcome again to another tutorial on Pari GP. So today I want to talk to you about some number theoretical functions that we can use in this program. So I'm going to start with something that we actually did before, which is look at the table of contents, if you want to call it like that, using the question mark. So it's going to give you a list of topics, and you can look at all the topics that we have right here. For the moment, we are interested in here in the number 5, which is the number theoretical functions. And I'm going to say question mark 5, and that will bring up the collection of number theoretical functions that are available in Pari GP. So there's a bunch of them, as we have seen before. Now let's start with something simple. So let's say, for example, you want to look at the binary representation of a number. So we just type binary, and you just put the number that you want the binary in. So let's say, for example, 10. So that will give me the binary representation of the number 10, and that is give that answer in a list. So the binary representation will be 1, 0, 1, 0 in binary. In this case, is given in a list. You can also check binary representation. It doesn't have to be whole numbers, be numbers that are not whole numbers. So say, for example, the binary representation of 10.22, and that will also give us the binary representation of that. So this first part, the first list, it will be the whole number part, and the other one will be the decimal representation of that number. Now, there's another way you can also look at representations of numbers. So for example, let's look at this function, which is digits. That's going to give you the digits of a number. So if we put something like 134, and because we are using base 10, it's just going to give me the list of the digits 1, 3, and 4, assuming that it's all in base 10. You can use digits also to find binary representations of numbers. So for example, if we want the binary representation of 134, so we just say digits 134 and then comma 2 to indicate that we want the binary representation of 134. So if we press enter here, that's going to give us the binary representation of 134. Digits, a number, comma 2 is going to have the same effect as binary of that number. Now let's look at something else here. So for this case, I'm going to clear the screen now, and let me use the variable. So I'm going to call x equal, and I'm going to look at the digits of the following number, 1, 21, and let's say we want base 16, so hexadecimal representation. So that's going to give me 7 and 9. That is in hexadecimal. So the number 121 is 79 in hexadecimal representation. Now, if you know that you already have 7 and 9 as hexadecimal, and you want to get back the number in decimal from that hexadecimal representation, you can use another function that is called from digits. And then from digits is going to give us the decimal representation of the number x. That's why I use the variable, so I don't have to type that much, x. And then 16, that's going to give us the decimal representation of 79, which is, of course, we expected that to be 121. Now, let me do a couple of things here. So I'm going to show you the Euclidean quotient and remainder. And for that, I'm going to use a couple of things. I'm going to use again the variable x. One other thing that you can also use in Pari GP is use the function random. So the function random here is going to give you a pseudo-random number in a range. So if you just say, for example, 100,000, that's going to give me a pseudo-random number between 0 and 100,000. So if I press enter, that's the number x, so 94,377. And let me use another variable y for random, and then let's look at a little bit smaller number. So let's look at the range from 0 to 1000. So in this case, y is 419. So the Euclidean quotient is with the backslash. So if I do x slash y, is going to give me the quotient of that division. So in this case it's 225, and the remainder is very standard, is with the percentage sign. That's going to give me the remainder of x divided by y, which is in this case 102. So that's a couple of things there. Euclidean quotient and remainder. Remember, this is for the remainder. It's Euclidean remainder. In this case, this computation here will always give me a positive remainder. So that's why it's called Euclidean remainder in that case. Now you have also some other functions. For example, the GCD, the greatest common divisor between two numbers. Let's say x and y, the numbers that we generated before, the random number that we generated before. So in this case is 1. You can apply the GCD to any pair of whole numbers and it will give you the greatest common divisor. The same is true for the LCM, so the least common multiple, let's say of x and y. So in this case, it's going to give us the least common multiple, which is that number that you see there. Now you also can get, and we haven't covered this in the number theory class, but there is something called the extended greatest common divisor algorithm, which is going to give you also two extra numbers. And for that, the function is called the GCD, the extended Euclidean algorithm, which is going to give us also the greatest common divisor plus a couple of numbers that are going to be the coefficients for which you combine them and you get the greatest common divisor. So the greatest common divisor will be the last number in that list, and this is going to be the coefficient of the x and the y. So if you multiply x by this number and y by this other number, you will get the greatest common divisor. So that is the explanation of the extended Euclidean algorithm. Now, we talked about this before, this function primes. So it's going to give us the list of primes. So let's recall that again. So primes, if we want a list of the first 200 prime numbers, you just type primes of 200 and we have the list of the first 200 numbers. Now, if you want a prime number in a specific position, so let's say you want the prime number, let's say the 20th prime number. So you just say prime 20th, and then it's going to give us the 20th prime number. So starting 1, 2, 3, and so forth. So the first prime number is 2, the second prime number is 3, and so on. So the 20th in this case is 71. Now there's also another important function. I'm going to clear the screen here. The other important function is the number of primes less than or equal to a specific number. And that is a common also number theoretical function, and that in Pari GP is prime pi. So prime pi here, what's going to do is going to give me the number of prime numbers less than or equal to whatever I input in there. So for example, if I put prime pi of 100, it's going to give me the number of prime numbers less than or equal to 100. So there are 25 prime numbers less than or equal to 100. Now 100 does not have to be a whole number, so it could be prime. So for example, some decimal expansion like that. So it's gonna give us 25 again because it's less than or equal to that. Now, so that's an important function that you will see in number theory a lot, the counting prime numbers. Now, another thing that we have seen already is how to check that a number is prime, and the function for that is prime. So whatever you put inside the parentheses here is gonna check for primality. Now, this function it gives you an exact answer. What I mean by that is whatever it says, that's the truth. So it's not a probabilistic answer. So whatever I put in there, it's gonna give me a precise answer. The draw point of that is that it could take between 50 and 30 minutes to check that something is prime if the input that you give it is a prime number that is about 1,000 digits. So if you have a prime number that is 1,000 digits is prime, is going to take a long time to decide whether or not that is a prime number. So in general, if you give it a small number that is not too big, it's going to make a decision quite quickly. Of course, that number is going to be non-prime, so it's going to give me 0 because it's even. Now, another function that also checks for primes is pseudo-prime. So that function also checks for primes. So is pseudo prime. I'm going to use the pseudo prime. That function, what it's going to do is going to check that something is a prime number, but is a probabilistic answer. And I'm going to explain what that means. So what that means is this. If this function returns 0, that means that the number that you put in parentheses is definitely not a prime, 100% sure. But if that function returns 1, it's very likely that the number is prime, but there's still a small chance that the number is not a prime. So let me repeat that again. If it is 0, it's definitely a prime. If it is 1, it's very likely that is a prime. Now, there is no known counterexample where you put something that is a composite number and is pseudo prime and you check it and it gives you that is prime. That has not happened. So we can check, for example, some number here is pseudo prime. So in this case, it's gonna give us that is not a prime. So 0, so that's definitely not a prime number. But if it gives us 1, it's very likely that it is, but there are no non-counterexamples. So you can also use that for check for primarity. So this one is faster, that is prime. That's the advantage. But the bad part, in a sense, is that it's a probabilistic answer. Okay, let's go into, for example, factorization, which is also very common in number theory. So I'm gonna say something like this. I'm gonna factor. So this is gonna factor an integer. So let's say everything, so 20 factorial plus 20. So that's gonna factor the number 20 factorial plus 20, which is 20 factorial, remember, is all the multiplication from 1 through 20 plus 20. That's gonna factor that number. And this is the factorization that it gives you. So one thing that you need to make sure here is that you understand the answer here. So the answer is the list of lists. This list right here, this sub list, what it says is this first number here is the prime and this is the exponent. So it's 2 squared times 5 to the first power times 71 to the first power times this number here, which is a prime number, to the first power. So every time you see the first component of the sublist, that is the prime number, and the second component is going to be the exponent. So just be aware that that is how this the answer is formatted for factor. So another function that you can also use here is omega. Omega is going to give you the distinct number of prime divisors of a number. So for example, if we say omega of, let's say, 120, that's going to give you the distinct number of prime divisors that number has, the number of distinct prime divisors. So it has 3 distinct prime divisors. And if you check the factorization, that's going to have 3 distinct prime divisors there. Now, you can also ask for the divisors of a number. So let's say divisors. And let's look at something like this, for example. So that's going to give me the list of all the divisors of any number. Now, if you don't want the divisors, but you just want the number of divisors, there's another function that is called num divisors, which is going to give me the number of divisors of a number. So let's say some number like that. And the number of divisors there is 24. So it doesn't give you the list, just the number of divisors of that number. Okay, let me clear here the screen again. And let's continue with another very standard number theoretical function that is called sigma, that adds all the divisors of a number, and that is in PariGP is called, as you can guess, sigma. So if you have sigma, for example, 121, it's gonna add all the divisors of that number. So that's 133. So it takes all the divisors of 121 and adds them all up. Now there's another function, so which is very similar to this one, that is sigma, the same notation again. But if you give it one more input, that's gonna be the sum of the divisors to a certain power. So for example, if I say sigma 121,2, that's gonna take all the divisors of 121, square each one of them, and then add them up all together. And that's that number. Of course, is bigger. So if you try something like 5, it's still gonna take all the divisors of 121, take the fifth power of each one of them and add them up, and then we get that number. So that's the function sigma. Another very popular function in number theory is the Euler phi function. In this case is Euler phi. And Euler phi, what it does is it counts the number of naturals relatively prime to whatever I input in the parentheses. So what I mean by that is this. So suppose I have, let's say, 45. So what is Euler phi of 45? Is all the natural numbers less than or equal to 45 that had only 1 as a common factor with 45. That will be the Euler phi function. So in this case it's 24. So there are 24 natural numbers less than or equal to 20 to 45 that are relatively prime to 45. So there's another popular number theoretical function. Let's move into, let's say, sequences. Now, one really important sequence is the Fibonacci sequence. So PariGP also has a way to find the Fibonacci sequence, which is called Fibonacci. So if you put Fibonacci, it's gonna give you the nth Fibonacci number. So the Fibonacci sequence is a sequence that starts at 1, 1, and the next number is the addition of the previous two. So 1, 1, 2, and then 3, and then so on. So if we ask for what is the 10th Fibonacci number, so the 10 in that position, that's 55. Now you can also ask for the list of things, and I think we have seen this in other videos about PariGP and a number theory class, which is we can do this using a list. So let's say, for example, I want all the Fibonacci, the first 10 Fibonacci numbers. So one thing you might do is Fibonacci of 1, Fibonacci of 2, but of course that's gonna take a long time. Instead of doing that, we're gonna make a list, and we make a list in PariGP with open square bracket and close the square bracket. So we're gonna put the generic thing here, the Fibonacci. So Fibonacci of n, that's gonna give me the n Fibonacci number, and I have to specify Fibonacci. I made a mistake. So Fibonacci there of n, and then I'm gonna put a pipe sign, which is gonna indicate that I'm gonna tell what kind of n's I want here. So I want my n's to be coming from the list. So this is less than sign and then a hyphen there, from the list from 1 to 10. So what that means is I want the list of the Fibonacci numbers of n, and that n is ranges from 1 through 10. So that's gonna give me the list of the first 10 Fibonacci numbers, 1, 1, 2, 3, 5, 8, and so on. Now, one advantage that you can get from this kind of notation is I can do a little change here. So let's say I want the first 20 Fibonacci number is gonna give me that first list. So that's a good thing about having these representations of list. Okay, one last thing I want to do is I'm going to give you a graph here. So what I want to do for the last part is I'm going to graph the number n against the number of divisors. Now you can draw points in Pari GP if you specify what are the values of x and what are the values of y. So let me do this. So I'm gonna call x, and x is gonna be my values of x, which is gonna be a list. So I'm gonna have a list from 2 to, let's say, 5,000. Now I'm gonna give this many numbers in that list because I want my graph to actually show something. If I give a small number, the points are not going to be visible. So that's why I'm choosing that many. Now, if I press enter right here, it's going to give me that list. I don't want to see it. I just want to assign it to the capital letter X. So I'm going to put a semicolon there. So it's still X is going to be that list, but it's not going to show it. I don't want to see that. This is going to be the values of X. Now my values of Y will be the number of divisors of 2, numbers of divisors of 3, number of divisors of 4, and so on, up to numbers of divisors of 5,000, because I want to plot X and Y with those two sets. So I'm going to make a list. Number of divisors is this, number of divisors of n, and the pipe symbol, because I'm going to make a list of number of divisors of n, and that number n is gonna come from the list from 2 to 5,000. Now I already have a variable for that. The variable is x, so I'm gonna use just the variable x. And in this case, I'm gonna use also a semicolon, so I don't have to see the result of that. I don't need to see that. I'm just doing this for the plot. So now I have the values of x, I have the values of y. And the only thing I have to do now is I have to plot the points. So to plot the points, we're going to use a function to plot, which is called plot h row. So the plot h row is going to take two lists. The first list is going to be a list of values of x, which I'm going to call x. I'm calling x here, and the list of values of y, which we are calling y here. So that's going to give me, it's going to plot all those points. So there's tons of those points there, right? So let's press enter here. And as you can see, we have the list of the plot of the list of that list of the values of x from 2 to 5,000 against the number of divisors. I don't know if you can see well here, but there are some horizontal lines there with that plot. All right, so that's kind of a cool thing to see, plot. And okay, that's all I have to say for today. Thank you for watching. Take care and good luck.